I don't know.
I'm trying to look at my syllabus.
Yeah, we have, quiz, then we have something, example exam, then we have exam. So, couple Wednesdays away. All right, today we're gonna do chemical bonding and nomenclature. We talked about molecular and ionic compounds. Today we're going to learn a little bit more about them, including how to name them. When we talked about molecular and ionic, we said that there were two basic differences. A molecular compound will look like this. It will have covalent bonds. Those are shared electrons between the atoms. And it will have a defined shape. Every molecule of methane, natural gas, will look exactly like this one. The bonds in a covalent compound can be single bonds, like we've seen here. We can also have double bonds and triple bonds. Every bond, remember, represents two shared electrons. The other alternative here was ionic. In an ionic compound, we have charged atoms. The charged atoms, positive and negative, cation and anion, simply attract each other. Now they do this in a they pack themselves in a very regular fashion, and because of that, they form crystals with a very predictable shape. It's basically just a long extended array. This is sodium chloride of sodiums and chloride, both as ions. Now when we did Lewis structures, we talked about how we made an ion, just for review. Remember, in a Lewis structure, for something like chlorine, chlorine is in the 7th group of our periodic table, so we know it's going to have 7 valence electrons. On the exam, you will be asked to draw a Lewis structure, so make sure you got this. As you are putting this together with your 7 valence electrons, remember they go in one at a time first, and then you pair them up. It doesn't make any difference where the unpaired one is, just as long as you have one unpaired electron. Now to make the anion, all we had to do was bring in an extra electron and indicate that the chlorine now has a negative charge. Any questions? Yeah.
Do we ever have to draw a structure for the transition metals in the middle?
Oh, for these guys? Probably not, because they can be very complicated. So we'll stick to the first 3 periods. But we are going to talk about the 3rd period and below right now, because as we were talking about Lewis structures, we pointed out that the whole point of the exercise here was to come up with an octet of electrons. And that makes an atom very unreactive. For hydrogen, 2 electrons because it's in the 1st period, but everything else here was shooting for 8. It's called the octet rule. Turns out, however, that there are exceptions to the octet rule. A classic example here is sulfur tetrafluoride. 1 sulfur and 4 fluorines. This is what it looks like. And as you look at this little sulfur guy has 2, 4, 6, 8, 10 valence electrons. So let's just take a second and see how this happens. Oh, the geometry of this, just to show that chemists do have a sense of humor, is called seesaw. Okay, SF4, as we did for the other molecules that we made, We start off by finding them on the periodic table. Sulfur is here in group 6. It will have 6 valence electrons. I arrange them like this, 2 pairs, 2 singles. Fluorine is over here in group 7, so it will have 7 valence electrons. So we start off by putting the 4 fluorines around the sulfur. Now, right away, we can look and see, yeah, we can make a bond here, that's no problem. 2 electrons lined up nicely, good bond. Same thing here. But in both of these, we have 3 electrons in between our atoms. And that's a little bit of an issue. So what I'm going to do, since Lewis structures are just bookkeeping tools, what I'm going to do is just take 2 of these electrons, there they go, and I'm going to put them in, quote, storage. So they're somewhere down here on the floor. All right? Now, by taking those guys away, it now becomes very clear how we can make 4 bonds to our sulfur. 1, 2, 3, 4, and we can just draw them in like that. But ethically, we know that somewhere down on the floor there's a pair of electrons, and they belong to that sulfur. So we've got to put them back. This gives us 2, 4, 6, 8, 10 electrons around our sulfur. This is known as valence expansion. Anything in the 3rd period down to the 7th, anything can have more than 8 electrons. They can have 10, 12, or 14 valence electrons. But those are more complicated. Once again, we're going to limit ourselves to the top of the periodic table. Any questions? Once again, this is what it looks like. Seesaw structure. And where are these electrons? They're in something called a hybridized orbital. In general chemistry, you may learn about hybridized orbitals. Basically, it's a mathematical combination of all the available orbitals, and this is called an sp3d orbital, a mathematical average, if you will, of the orbitals. Let's do one more here. BH3, boron with 3 hydrogens. Now, you guys just saw me do SF4. Go ahead and write down the boron. Boron is here in the 3rd group. So you're going to have a B, and you're going to have 3 electrons around it. Now, hydrogen is over here in the 1st group. So it has 1 valence electron. We have 3 of them, so we'll put them around our boron. Now, clearly we can make bonds here, here, and here. But when we do this, our poor boron is stuck with only 6 electrons. Now, this can happen. Lewis structures can wind up with 6 electrons around the central atom, 7 electrons, but we try to shoot for 8. That's because 6 and 7 are very unstable. More boron, however, is stuck with our 6. You will learn in general chemistry that this makes it what's called a Lewis acid. Lewis acid is an electron acceptor. Think of boron having a giant hole right here. Dearly wants electrons. So it's an electron acceptor. Very powerful thing. Any questions? go back to ionic compounds, and we're going to learn how to name them. There are some rules that go as far as constructing them, and once we construct it, then we can name it. As I said before, we have cations and anions, positives and negatives. In this case, chloride anion, sodium cation. Like I said, these things pack together like little balls, and depending upon the actual size of the element, you can pack them together in various ways. You tend to always go for the most efficient packing. And in this case, for sodium chloride, it's cubic. So these are arranged in a cube. You can see that in the actual crystal. This is a nice crystal of sodium chloride. You have sharp edges, nice cubic shape to the crystal. Again, it's just a big array of these guys, on and on and on. Held together because electrostatically, one's positive and one is negative. All right, we're going to make anions and cations. If we just look at the periodic table, turns out that it's very simple to predict the charge that you'll have for the representative group elements. For the first four, it's simply the group number is the positive charge associated with it. So group 1 is +1, these are all +2. Over here we would be +3, and if these were ionic, they would be +4. Now once you get past the fourth group, it becomes more advantageous to the element to add electrons to try to get to 8. So over here, starting in group 5, we're going to add 3 electrons, 2, and then 1. So just by finding somebody in the periodic table, you can have a pretty good bet as to the charge that the ion is going to have. Secondly, when we go to build an ionic compound, we have to make sure that it's neutral. Now this is called the principle of charge balance. Charge balance simply means that the charges on the cation plus the charges on the anions must add up to 0. Here we have magnesium with a +2, sulfur with a -2. Again, they add up to 0. That's your net charge. +1, -1. If we're going to pair sodium with sulfur, sulfur is -2, so we need 2 sodiums to make it overall neutral. Likewise, magnesium with a +2, if we paired it with bromine, bromide from the 7th group, we're going to need 2 of these because they're -1, again, to give us a net charge of 0. So that's the first thing. Secondly, when we go to write our compound, we have to make sure that we write the thing using the simplest whole number ratio of the elements. Simplest whole number ratio. So here, for our magnesium with sulfur, this is 1:1, we would just write MgS. If you had written Mg2S2, that's wrong. Mg4S4, that's wrong. Lowest whole number ratio. For 1 sodium, 1 bromine, sodium bromide. Now here we have 2 sodiums. We show that using a subscript after the element, and we write sodium, there's 2 sodiums for every sulfur. Likewise over here, we need 2 bromines for every magnesium, So we put our 2 out here. Any questions? Being able to look at a formula and read it like this is an important skill that you'll need for the first exam. So make sure this works. When you are looking at a compound and you're trying to figure out the atoms that are in there, again, you simply take the formula and read it backwards. This is 1 sodium, 1 chlorine, 1 hydrogen, 1 fluorine, 2 hydrogens, 1 oxygen, 2 potassiums, 1 sulfur, 4 oxygens. Simple way to do it. We'll see in just a little bit that when you, there will be instances where you will have to place a unit in parentheses. If you have more than 1 unit at a time, they're called polyatomic ions, and we'll do those in a few minutes. Any questions? All right, well, let's build one. Magnesium and chlorine. Very quickly, write a formula for this compound. Step 1, you have to find them on the periodic table. Magnesium is here in group 2. Chlorine is over here in group 7. So, magnesium will be +2, and chlorine will be -1. Now we need neutrality. So to make this neutral, we're going to need enough Cl minuses to balance out the +2 charge here. Very simple to do. We need 2 minuses for our +2 ion, MgCl2. Most ionic compounds you can just write simply by inspection. Look at the charges, put them together, make it neutral. Now sometimes compounds can be a little more complicated. Let's look at aluminum and oxygen. Go ahead, find them on the periodic table, and then write a neutral compound. Aluminum lives here in the 3rd group. Oxygen is here in the 6th. So aluminum is going to be a +3. Oxygen will be a -2. Now what we have to do is come up with a ratio of aluminum to oxygen so the net charge is 0. Now, I'm sure everybody in this room can do this. Not that complicated, but there is a trick. There's a little symmetry trick that I'm going to show you that works nicely. We have aluminum with a +3 and oxygen with a -2, right? Imagine that these were more complicated if you want, but just write down your elements. The 3 from the aluminum is going to transfer down to the oxygen. The 2 from the oxygen will transfer down to the aluminum. So it's a simple crisscross. Crisscross symmetry. 3, 3, 2, 2. Think about it. This is 6 positives. This is 6 negatives. Now, this is a nice little tool for complicated molecules. You don't want to use it blindly. For instance, go ahead and write beryllium and selenium. Beryllium, right here in group 2, +2. Selenium, over here under sulfur, group 6 minus 2. Now we can all do this in our head. Plus 2 and a minus 2, that's pretty simple. But if for some reason you did your crisscross here, you would come up with Be2Se2. And of course, that's wrong, because you need the lowest whole number ratio. So if you do the crisscross, look at your answer, make sure it meets the criteria of lowest whole number ratio. Any questions?
So what would have been the correct one now? B?
Yep, this is the correct, 1 to 1. This is what it looks like, actually. Little tiny berylliums, big seleniums. It's a semiconductor. All right, let's go ahead and name these things. Naming for ionic compounds is really, really simple. Really simple. Actually, naming for all binary compounds is simple. But for an ionic compound, you're going to build the name starting with the cation. That's the charge thing, right? Positive charge. You're going to simply put the name of the element. That's one word. This is magnesium. So for our first word, we would write magnesium. That's it. Second word, we look at the next element. This is the anion. And you try to figure out what the root of the element is. This is bromine. The root is going to be brome. Okay? So we do magnesium, and then we put in brome. To show that it's our second element, we're going to add the suffix IDE to this root. And this becomes magnesium bromide. The first word is just the first element, period. Second word, you get the root and you put IDE on it. Multipliers are not utilized. There are 2 bromines here, but we don't say that there are 2 bromines. You are just supposed to know that. Now that makes going backwards a little more difficult, but going forwards is really simple. So do this one. Our first element is just what? Sodium. The root for chlorine is going to be what? Chlor. And to show that this is the anion, we add IDE. K is what? Potassium, right? Don't forget that one. This is sulfur. What's our root going to be? Sulf. And to show that the sulfur is the anion, we add IDE. We just did beryllium. This is again bromide. Any questions? Yeah, I told you that was simple.
Yeah, okay.
Do a batch. You'll see how simple they are. I will pace back and forth for a moment and let you get a head start. Ca is calcium, that's our first word. The root is brome, and this is therefore calcium bromide. We did this guy, Al2O3. Al is aluminum, and that's our first word. This is oxygen. The root is going to be ox, and we add IDE. Aluminum oxide. Li is lithium. That's our first word. This is sulfur. Our root is sulf, and this is sulfide. Calcium again. Oxygen again. Oxygen, we said, was simply oxide. And finally, this is nickel, isn't it? This is chlorine, so just like we saw before, this is going to be chloride. Now it turns out that that name is actually wrong. And we'll find out why it's wrong in a few minutes. It's wrong because nickel lives up here in the transition metals, these guys in the middle. The interesting thing about most of the elements in the transition area is that they can have multiple charges, but the representatives that are associated with the groups. But we'll see that elements in the transition region can have multiple different charges, +2, +3, +4, whatever. So this, we need to actually say which nickel this is, and we'll see that this is called nickel 2 chloride to show that it's a +2. You can tell it's +2 because every chlorine is -1, isn't it? So this has to be +2 to be neutral. But we'll do that in just a minute. All right, let's work backwards. This is where it gets more difficult because you're expected to know the charges and be able to write the compound. You don't have multipliers to help you. Well, calcium is over here in our second group, so it's a +2, isn't it? Nitrogen is over here in the fifth group, so it's going to be a -3. So now is when you need to take the +2 and the -3. You can crisscross them if you want to come up with a neutral compound. We're going to need 3 calciums for every 2 nitrogens, and it will look like that. Just think about the charges. This is +2, so this is 6 positives. Nitrogen is -3. This represents 6 negatives. Magnesium oxide. Look at your periodic table and find magnesium. It's right there in group 2. Oxygen is over here in group 6. So it will be a -2, magnesium, a +2. To get our lowest whole number ratio and a neutral compound, we would need 1 magnesium and 1 oxygen. Lithium iodide. Lithium lives over here in group 1. so it's a +1. Iodine lives here in group 7, so it will accept 1 electron, making it a -1. Once again, we have a 1-to-1 ratio, and we simply write LiI. Looks like a little, but barium phosphide. Look at your periodic table. Barium is in our 2nd group, so it's a +2. Phosphorus is over here in the 5th, so it's going to need 3 electrons. It'll be a -3. Once again, +2 -3, crisscross, we need 3 bariums, 2 phosphorus, 6 positives, 6 negatives. And finally, beryllium fluoride. Beryllium, once again, is in our 2nd group, so it's a +2. Fluorine is over here in the 7th group, so it's a -1. We're going to need 2 fluorines for every beryllium, and we would write it like this. Any questions? All right. Well, this is one of those instances where just when you can sit back and say to yourself, I think I got it, right? Then you get the curveball, sort of. Turns out that there's another ionic thing that we need to worry about. And this is called a polyatomic ion. Polyatomic ion, for example, strontium sulfate, is going to consist of 1 strontium with a +2, and one thing, the polyatomic ion part, that we call sulfate, is a sulfur with 4 oxygens bonded to it, and these are all covalent bonds. The whole thing has a -2 charge. Think of it as a ball. We have one of these guys and one of these guys as units. Now, the sulfate actually looks like this. There's our sulfur in the middle, 4 oxygens around it. And when you pack them together, the sulfates stay as these lumps with the strontiums all around there. Now, there turns out to be lots and lots of polyatomic ions. As we talk about them, you get to know the ones that we use a lot. And of course, the ones we use a lot are the ones that you need to know. Now, unfortunately, there's no simple way, there's no song you can sing, there's nothing to help you remember all of these. But remember, on your exam, everybody is allowed 1 3x5 card. 3 inches by 5 inches, not 3 feet, but 3x5 card. And you can write anything on it you want, anything. Now, I think that by the time we do the exam, you'll be familiar enough with these that you don't want to waste the card on that. But if you wanted to, you can write these guys down. Card is nice, it relieves a lot of stress, and teaches you to write very, very small. Okay? Turns out that there's a fairly simple way to remember simple polyatomic ions. We're dealing here with oxygen containing, that means there's a different atom in the middle, and oxygen on the outside. The parent, we're gonna stick 8 as the suffix. I said we were dealing with sulfate, right? Sulfur. Root is sulf. We stick 8 on it. Sulfate. That is the parent compound. If we have one extra oxygen around our sulfur, we would call this a per-sulfate, with the per in front. If we had one less oxygen, we'll change the 8 to an ite. If we have 2 less oxygens, we put a hypo in front and call it hypoite. But the neat thing is that within this entire family, all of these are going to have the same charge. So let's look at a real example. Chlorine. The parent here, the root is chlor, right? So the parent is going to be chlorate, right here. ClO3, 1 negative charge. If we add 1 extra oxygen, we get perchlorate, same charge. 1 less oxygen, we're chlorite, same charge, and 2 less, hypochlorite. Hypochlorite, sodium hypochlorite, is bleach in a OCl. Again, here's our parent. 1 more oxygen, 1 less, 2 less. For sulfur, our parent, like we said, was sulfate. We take oxygen away and we have sulfite. Turns out that in many polyatomics, see these oxygens have charges, don't they? We can actually neutralize one or both of those charges by sticking a hydrogen on. If we do that as a polyatomic ion, we simply stick the word hydrogen in front and then the ion. So this is sulfate, this is hydrogen sulfate. Sulfite would be SO3, hydrogen sulfite, HSO3. Phosphorus, phosphates are parent. 1 less, phosphite. We have 3 oxygens we can put hydrogens on. So we just do it hydrogen phosphate or dihydrogen if we have to. Carbon. Carbonate's the parent. There is no carbonite. That was in Star Wars. Put a hydrogen on, hydrogen carbonate. Acetate you really won't use until you hit general chemistry. Cyanide is nice to know because it's everybody's favorite poison. Carbon-nitrogen triple bond with a negative charge. Any question? Nitrogen, we'll do a lot of nitrogens. Nitrate, NO3, nitrite, NO2. Now the only positively charged polyatomic we're going to deal with, probably you would not deal with anything else until you hit general chemistry, but this is ammonium. Ammonia, NH3, right? We've done that, we drew its Lewis structure. If you put another hydrogen on, you get a positively charged thing we call ammonia. Now this might seem a little overwhelming. Again, you have a card if you get lost, but I think that as we do these things, it will become very obvious. I said that polyatomics have covalent bonds and a charge. I think it's constructive just to look at the Lewis of one of these things to see how this happens. So let's do chlorate with a single negative charge. Now, again, make sure you know how to construct a molecule. That's what you're going to do on the exam. Make sure you understand this. You're going to find the atoms in the periodic table. Chlorine is here, group 4, or chlorine is here, group 7. So we will have 7 valence electrons. Oxygen, group 6, it will have 6 valence electrons. So we put our chlorine there with 7. We're going to put 3 oxygens around it. Now, first thing I do is I look at this and say, well, this is ugly. Because we've got 3 electrons here between these Cl's and O's. Because Lewis structures are just bookkeeping, we can move those around. That's no problem. So if I want to take this electron and move it up here, I can. Likewise, take one of these, move it up here, I can do that. Pair these 2 up, I can do that. That's all legal. And I just did it. Now, if you look at what I've written, you can see why I did it that way. Because we have 2 electrons here to make a bond, don't we? We have 2 here, only 1 here. Oops. But, no problem. Remember, chlorate has a single negative charge. So, we're going to take this electron from space somewhere, stick it here on the chlorine, and suddenly we have 2 electrons here to make a bond, just like we do here and here. Scooch them all together. Every oxygen has 8 electrons around it. The chlorine in the middle has 2, 4, 6, 8 electrons around it. We can draw it this way with our lines. And again, this whole unit with these 3 covalent bonds has a -1 charge. Any questions? So that's how you put it together. And that's how the things wind up with a charge, because we add an extra electron or 2 or 3. All right, name these guys. Well, we're going to do this exactly the same way, aren't we? Going to write our cation first. That's calcium. And now we either scratch our head and say, what the heck is CO3? Or we just look at our sheet. Or we remember, my gosh, that's carbonate. Calcium carbonate. 2 words. Remember, NH4 was our cation polyatomic, +1 charge. We call that, because it's a derivative of ammonia, we call it ammonium. The anion here is just chlor, so that's chloride. And the name is ammonium chloride. Sodium, that's our first word. What's SO4? We've seen it several times now. SO4 sulfate. If this is sulfate and we take 1 oxygen away, what's that? Sulfite. The cation is lithium. Now, PO4 is phosphate, isn't it? We have a hydrogen in there. That's going to be a separate word. And the cation here is potassium. So we'll simply write potassium, hydrogen, phosphate. 3 words. Yeah,
We will suffix for 2 less oxygens.
I'm sorry?
The suffix for 2 less oxygens? Was that
Hypo something, height. So if chlorate is ClO3, chloride is ClO2, and hypochlorite is ClO. All right, let's go backwards. This is even more difficult. Lithium is Li. That's the simple part, right? We just did chlorate. That was ClO3. Right? Perchlorate is what? 1 more oxygen. ClO4. Lithium is +1. The chlorate family is -1. That's it. When you see this, you immediately think to yourself, chlorine in the middle, 4 oxygens around it, -1 charge. Any questions? Okay. Barium sulfite. Barium is Ba, it's a +2, right? Our sulfur family is a -2, so that's convenient. If sulfate is SO4, sulfite is 1 less, it's SO3. Aluminum, we've seen aluminum many times, it's a +3, isn't it? The chlorine family, chlorate is the parent, it's a -1. Now to make this neutral, how many chlorates do we need? 3. We have a +3, we need 3 negatives, right? How do we write that? Well, aluminum is the easy part. Every one of these guys is a -1. And so we need 3 of them. We take the whole unit, put it in parentheses, if we need more than 1 of them. 3 chlorates with a -1 each. Now, silver nitrate. If you look at the periodic table, silver is right there. It's a transition metal. So this isn't a ringer, I suppose, but silver is always +1. It's always +1. Don't worry about it. Nitrate, this is our nitrogen family. It's the parent. NO3 -1. 1 silver, 1 nitrate. And finally, barium cyanide. Remember cyanide, carbon nitrogen triple bond, -1 charge. Barium is a +2. So we need 2 cyanides. Think about how you write this. We need 2 of them. So the cyanide has to be in parentheses to show that we have 2 of them. And it looks like this. Each side adds a -1, and we need 2 of them. All right, this just takes practice. We'll do practice. Don't worry about that. Quickly, let's look at these. Name the first one. Pb is lead, right? O is oxygen. That'll be oxide. So we could write lead oxide. Everyone happy with that? Pb is still lead. Oxygen is still oxide. We don't use multipliers. So that's lead oxide too. Fe is iron. This is oxide. That's iron oxide. And so is that. And so is that. Well, clearly we have a problem here, don't we? This is what I was saying about transition metals. Remember, transition metals can have different charges. And because they have different charges, we're going to have to be able to put the charge into the name. So anything down in this region right here, we have to worry about what its charge is going to be. First thing you do when you find a name is figure out if you're dealing with a transition metal. We're going to deal with a concept called oxidation number. Now I'm going to introduce the words. In chapter 5 or 6, we're going to do reactions. And one type of reaction is going to deal with oxidation and reduction. So we're going to need to know a lot about oxidation then. Right now we don't. Oxidation number basically is going to be the charge on an ion. For example, if we have magnesium bromide, the charge on magnesium is +2, charge on bromine is -1. In oxidation terminology, we simply say oxidation number of magnesium is +2, bromine is -1. Same as the charge. Lithium phosphide. Lithium +1, phosphorus -3. Simply use a different word and describe the charges as oxidation numbers. Now, when we hit chapter 5 or 6, we're going to learn a whole set of rules for assigning oxidation numbers. They look like this, but for right now, all you have to remember is oxygen is going to be -2, halogens, that's group 7, are -1. That's all you got to know. Oxygen -2, halogens -1. So let's go back to our dilemma here. This is lead oxide, right? What's the charge on the lead? Well, if oxygen is always -2, this to be neutral, lead must be +2. This oxygen still wants to be a -2. So this is 4 negatives. What's the charge on our lead? 4 positives. That's how you use oxidation numbers to figure out the charge. How about this? Sulfate, we know is always, it's a lump. It's always -2. That means the oxidation number or the charge on iron must be +2. The next one here. Oxygen is going to be -2. There are 3 of them, so that's 6 negatives, right? To make it neutral, we need 6 positives. We have 2 ions. They must be 3 each. All right, so how do we put this in our name? We saw it earlier for nickel. What you're going to do is figure out the charge, put it in parentheses in Roman numerals immediately after the cation. No space. No space. That's important. So, if oxygen is -2, we have 4 negatives here. The lead must be +4, right? We would write lead 4 oxide. No space. No space between the lead and the parentheses. Here we said oxygen is -2. That means this lead must be +2. So this is lead 2 oxide. The carbon family is -2. So CO3 is a -2 charge. That means the iron must be a +2. Iron 2 carbonate. And finally, bromine is a halogen. It's in group 7. It will always be -1. We have 3 of them. That's 3 negatives. The iron here must be +3. Iron 3 bromide. Any questions? How do you learn all of this? Well, like I always say, you practice. We will have 3 tutorials on nomenclature. In this one, you're going to be given a compound, ionic compound, and you're going to enter the name. Doesn't matter if you use capitals or not. If you need to put the charge, make sure you put the charge in properly, in parentheses. Make sure you put your spaces in properly. This is barium, isn't it? So our first word is just going to be barium. This is iodine. The anion is therefore iodide. And you type in barium iodide. I forgot to point out this is not a transition metal, right here in group 2, so you don't have to worry about the charge. Let's do another one. Copper and an iodine, right? Copper, there's a right there. It's a transition metal, isn't it? So we need to put in the charge. Iodine, group 7, so it'll be a -1. For this to be neutral, copper must be +1. So we will write copper 1 iodide. Once again, no space here. space in between. If you get the spaces wrong, it will blow up. One more. ClO. That's the chlorine family with 2 oxygens missing. So what's that called? Hypochlorite. And it's a -1. We have 3 of them. If each of these is -1, the iron must be +3. And so the name is going to be iron 3 hypochlorite. That's simple. Do it 1,000 times, you'll get it. Any questions? All right, well, we know what to do with ionic compounds now. How about molecular compounds? They're going to be exactly the same, except that with molecular compounds, we're going to use multipliers. That's going to make it so much easier. 1 is mono, 2 is di, 3 is tri, tetra, penta, hexa, hepta, octa, nona, deca. Now you probably should know the property one here. You do not use mono for the first element if there's only 1. If there's 2 of our first element, you use di, 3, tri, etc., etc. But you never use mono for the first element. Aside from that, that's the only rule you have to remember. Show you how simple this is. CCl4. We have 1 carbon, don't we? But we don't use mono for the first element. So the first word of our name is simply going to be carbon. Now we have 4 chlorines. Chlorine is chloride. How do we say 4 in chemistry? Tetra. This is carbon tetrachloride. 2 words. Told you it was going to be simple. One sulfur, 2 oxygens. Our first word is going to be sulfur because we don't use mono for the first element. Oxygen is oxide. How do we say 2? Di. This is sulfur dioxide. N2O. Now we have 2 of our first element, right? So we have to use a multiplier here. 2 is di. All we're going to do is call this dinitrogen. Now, oxygen here is going to be oxide, but there's only 1 of them, right? So we're going to call this monoxide. Now you may, if you're counting, there's an O missing. If you have a couple vowels thrown together like that, you drop one of them. I'm not gonna get you on that, don't worry. But you don't want two vowels. Can't say it. In 205, quickly write down this thing. What is 5? 5 is a pent, isn't it? Our first word, because we have two nitrogens, is going to be dinitrogen. We have 5 oxides, so we'll call this pentoxide. Once again, the AO kind of went away and just made pentoxide. Any questions? All right, let's do a set. This was on an exam once. Quickly write these guys. Our first one, we have 1 carbon. We don't use mono, we're just going to put carbon. We have 2 oxides. We will call this dioxide. We have 2 hydrogens, don't we? So we're going to call that a dihydrogen. Now we have 1 sulfur, so that's going to be a monosulfide. We have 1 silicon. So we're going to simply call that silicon. For hydrogen, the root is hide. Going to make it the anion, so it's hydride, second element. And we have 4 of them. So silicon tetrahydride. Sulfur and 3 oxides. Sulfur trioxide. Nitrogen and 3 chlorides, nitrogen trichloride. Now, one of these is going to be on your exam. So quickly do those. P is what? Potassium. P is phosphorus, right? And we have 4 of them. So we're going to call this tetraphosphorus. And we have 6 sulfides. 6 is hexa. Tetraphosphorus hexasulfide. Two iodines. So we're gonna write diiodine. And what's 7? Hepta, right? And we're gonna have AO, the thing again. So we'll just call this diiodine heptoxide. Yeah.
Don't get rid of the I.
No. No.
Okay.
That's an exception. I never thought about that. 1 oxygen, 2 fluorides, oxygen, difluoride. Now we've seen this guy many, many times. We call it methane, right? Or natural gas. Systematically, it's going to be 1 carbon and 4 hydrogens. So 4 hydrides, carbon tetrahydride. And finally, 4 sulfurs. 4 is what? Tetra. 2 nitrides, dinitride. Tetrasulfur, dinitride. Now, the fact that we use multipliers makes this drop dead easy to go backwards, right? 1 nitrogen, 3 iodides. 2 phosphorus, 5 oxygens. 1 sulfur, 3 chlorine. 1 nitrogen, 1 oxygen, just say no. 1 hydrogen, 1 chlorine. Later on in chapter 8-ish, when we talk about acids and bases, we'll see that this is actually hydrochloric acid. Any questions? Well, I'm sure the burning question is, where's the tutorial? There it is. In 203. Go ahead and write it down. N2 is going to be dinitrogen. This is oxide, and we have 3 of them. Dinitrogen, trioxide. NS. Real. First word is nitrogen, isn't it? We have 1 of our second element, so it's a monosulfide. And once again, you can do these all day. This is for molecular compounds. Turns out that there's another one simply called named formula that has both ionic and molecular. Now with this guy, you're given a name and you simply enter a formula. Now, clearly you can't do superscripts and subscripts and stuff like that. So just write it out like this, all in one line, and it'll figure it out. So, sulfur, tetrabromide. Sulfur is an S, tetra is 4, and this is Br. This is 1 sulfur, 4 bromines, and you write it like that. Do this one before I say anything. We remember from our polyatomics that phosphate is a -3. Sodium, of course, is a +1. So since phosphate is a -3, we're going to need 3 sodiums to neutralize it. How do we write this? Na3PO4. Remember, if you need to put something in parentheses, here's the example up here. Just put in your parentheses, just like that in that format. Any questions? All right, we know how to name now, both ionic and molecular. What we're going to do next is a very simple introduction to polar covalent bonds. And these are going to become very, very important to you when we start talking about solutions, acids, bases, things like that. So this is just a simple introduction, pretty pictures, interesting concept. Hard stuff's over. Dipoles. We have talked about covalent bonds where we have shared electrons. And we have talked about ionic bonds where we have totally transferred the electron. If you have 2 chlorines together like this, the sharing is perfect. The electrons are shared equally between both atoms. But for most covalent bonds, that's not the case. Consider hydrogen, H2, and hydrogen fluoride, HF. They're both molecular compounds. They both have a covalent bond. Now, in today's world of computers, we can actually calculate where the electrons are in a molecule like this. We can show that in what's known as electrostatic potential map. Electrostatic potential map, we'll use these later, but they're colored in a spectrum everywhere from red to blue. And that indicates electron distribution. Let's look at hydrogen first. What you do is you start off with your basic molecule, your 2 hydrogens, and you tell the computer to calculate where the electrons are around them. And it will do it. And you wind up with a nice little egg like this surrounding our 2 hydrogens. Next, you ask a question about the electron density. And it will then color this. For hydrogen, it comes out a really nice, slightly egg-shaped green ball, sort of. This tells us that the electrons are spread out evenly around these 2 hydrogens. Okay? Let's do the same exercise here for hydrogen fluoride. We're going to first calculate where they are, and then calculate the electron distribution. When we do this, we get something that's totally different. Blue represents the absence of electrons, or a positive charge. Red represents lots of electrons, or a negative charge. When you look at this and the shape here, obviously this fluorine, which is right here, is sucking all these electrons away from this poor hydrogen, leaving it electron deficient, and is here basking in this huge electron cloud. This is called a polar covalent bond. Polar covalent bonds, we'll see, are very important to us because they can be easily broken. We can show a polar covalent bond using what's called a dipole. Dipole is simply an arrow with a cross at one end. You don't have to color it, but it shows a positive end here and a negative end here along with this covalent bond. That's our dipole moment. Now, why does this happen? Doesn't seem fair, does it? Fluorine gets all the electrons. Why does it happen? It has to do with a property called electronegativity. Linus Pauling, the vitamin C guy, he's dead, developed this in the 40s, this concept, and basically assigned a number anywhere from 0 to 4 to elements in the periodic table describing how powerfully they attract electrons towards themselves. The trend, very simply, these are very low, fluorine is the highest, it kind of ramps up this way. Within any group, it ramps as you go up. Again, the highest. For HF, this is 2.2, this is 4. That's why fluorine is sucking the electrons towards itself. Now, there's a lot more to the story, but this is all you need to know right now. Just the concept of electronegativity, how powerfully an atom can attract electrons towards itself. All right. One of the things that's very important once you understand polarity of covalent bonds is molecular shape. We're going to talk very briefly, and we're just going to look at pretty pictures about molecular shape, just so you have an understanding of it. Actually, this is not on the exam, but you have to listen anyway. This is methane, CH4. We've seen this before. This geometry here is called tetrahedral. Tetrahedral is something they don't teach in kindergarten, but they should. All of the angles are 109. The element in the middle is suspended, equidistant from everything else. This is ammonia. Angles here are 107, kind of a little pyramid shape. This is PF6. That's 2, 4, 6, 8, 10 electrons around the 4 phosphorus in the middle. These are axial bonds, are called 120 degrees. These are 90 degrees. These two are the axial, equatorial. There's a simple theory that's used to describe how a molecule achieves its geometry. And it's the valence shell electron pair repulsion. And the basic premise is these electron pairs are charged, and they want to be as far apart from each other as they can. So, if we have 2 pairs of electrons in orbitals, they're going to want to be here and here. That's 180 degrees, isn't it? And that's a straight line. If we bring in a 3rd pair, so something comes in from the ceiling here, these guys are going to go down to get away from it, and you wind up with a plane triangle. And if we bring in a 4th one, we wind up with tetrahedral. This is a little movie, let's play it. We start off at 180 degrees, Bring our third one in, we're 120. Bring our fourth one down, and that's tetrahedral. So it's a simple concept. Let's explore this just a little bit more. Again, linear geometry, as far apart as they can get. Three things. We form a triangle, 120-degree angles. Four things. Stick the other one on top, push these down a bit, we get a tetrahedron. Now, within a tetrahedron, this is just to show what a tetrahedron is, in case you forget. Again, this is suspended equidistance from all four corners. Triangle and a straight line. All right. Let's take this very simple principle and see if we can predict the structure, the 3D structure of ammonia. Ammonia is NH3. The way we do this, and this is on the exam, something like this. First thing you want to do is draw a Lewis structure for ammonia. Make sure you can do this. Make sure you know how to do this. Just look at the periodic table. Nitrogen is in group 5, has 5 electrons around it. We have 3 hydrogens. They have 1 electron each. We're going to put those around our nitrogen, and we're going to make this. Make sure you can do this. Next thing we do to figure out the geometry is we're going to count how many electrons there are around this little nitrogen in the middle. Well, we have this pair, this one, and these guys. That's 4 of them, isn't it? How do we arrange 4 so they're as far apart as possible? As a tetrahedron. Therefore, it's going to look like this. The lone pair is going to be one of the corners of the tetrahedron, and these 3 things pushed out. Now, as far as looking at this, we would say, gee, kind of looks like a little tiny pyramid, and it does. It's pyramidal structure. But as far as electron pairs goes, it's tetrahedral. Do this one more time for something that's going to be very important. Oh, well, so here we go again. This is it. Again, this is how it fits in the tetrahedron. Again, dangling in the middle. Do water. Again, wipe the Lewis structure. Oxygen is group 6. It has 6 electrons around it. 2 of them are unpaired. Hydrogen has 1 electron. We want to stick them together, pair it up, and that's what you should do. Something like that. Doesn't matter where you put the hydrogens. Once again, our next step is to count, right? How many electron pairs around the oxygen? 8 electrons, 4 pairs. What's our electron pair geometry then? Tetrahedral. So what does water look like? This. This is 1, 2, 3, 4. couldn't see the electrons, you would just look at that and you would say, gee, it looks bent to me. And it is. It's called bent. This is what's going to be so very important to us for understanding water, acids, bases, whatever. Water isn't straight, it's bent. That means that these bonds, which are also polar, result in a molecular dipole. And that's what makes water a polar solvent. Yeah,
Can you go back a slide, please?
I think. Water doesn't look like this in a straight line. Water is bent. All right, so for our tetrahedral family, we can actually have 3 cases, something like methane, where we have 4 bonds, tetrahedron. Ammonia, we have a little pyramid here, 3 bonds and a lone pair. And water, 2 lone pairs and 1, 2 bonds. That's our tetrahedral family.